Let's look into the few more types of permutation tests and wrap this permutation test up. So there are two types. That's basically exhaustive and bootstrap permutation tests. In addition to the preceding random shuffling procedure, that shuffling procedure, we also call it as a random permutation test. We call it as a permutation test. In addition to that, people call it as a random permutation test or a randomization test. There are two variants of the permutation test. One is exhaustive permutation and second one is bootstrap permutation test. One is exhaustive permutation test and second one is bootstrap permutation test. So before we jump into this, let's understand no let's before we jump into the bootstrap permutation test, let's understand the exhaustive permutation test well. So in an exhaustive permutation test, instead of just randomly shuffling and dividing the data, we actually figure out all possible ways it could be divided. This is practical only for relatively small sample sizes. With a large number of repeated shufflings, the random permutation test results approximate those of the exhaustive permutation test. So, and approach them in the limit. So, exhaustive permutation tests are also sometimes called exact tests due to their statistical property of guaranteeing that the null model will not test as significant more than alpha level of the test. That's nothing but the statistical significance. Maybe how much you take, 0.05, that's fine. So an exhaustive permutation test involves considering all possible permutations of the data to create a distribution of test statistics under the null hypothesis. This approach is only feasible for small data sets as the number of possible permutations increases exponentially with the sample size. However, when it is possible to consider all possible permutations, the exhaustive permutation test provides an exact test with the guaranteed type 1 error control. And the second one that we have here is bootstrap permutation. So in bootstrap permutation test, the draws outlined in step 2 and step 3 of the random permutation test are made with a replacement instead of without a replacement. This we have discussed. In short, we call it as bootstrapping. See this two steps na. Shuffle the combined data and then randomly draw without replacement. If it is without replacement, it's called permutation test, and if it is with replacement, it's called bootstrapping. So in bootstrap permutation test, the draws outlined in step 2 and 3 of the random permutation test are made with replacement instead of without replacement. So in this way, the resampling procedure models not just the random element in the assignment of treatment to subject, but also the random element in the selection of subject from a population. So both procedures are encountered in statistics, and the distinction between these is somewhat convoluted and not of consequence in the practice of data science. So a bootstrap permutation involves randomly sampling from the original data to create a new data sets and then permuting the labels in each new data set to create a distribution of the test statistics under the null hypothesis. So this approach is computationally efficient and can be applied to larger data sets but may not provide exact type 1 error control. So if you want to have a type 1 guaranteed type 1 error control, you need to go for the exhaustive permutation. So if you are not much worried about the type 1 error control, you can go for the bootstrap permutation. So both exhaustive and bootstrap permutation tests are powerful techniques for testing hypotheses when the assumptions of parametric test are not met, or when the underlying distribution of the data is unknown. So they can be used to test for differences between groups or conditions, or to test for the presence of a relationship between the variables. So now the choice between exhaustive and bootstrap permutation tests depends on the size and the complexity of the data set, as well as the research question and the availability of computational resources. So exhaustive permutation tests are preferred when feasible, but bootstrap permutation tests may be useful alternative when the data set is too large for an exhaustive test. So now the next question that arises in our mind is what is the bottom line for data scientists? At the end of the day, whatever I teach, so what a data scientist will get from it, that's what my main agenda. So if there is nothing to be catered from respective domain, then there is no point of teaching that topic itself. So the bottom line for data science, what is the bottom line for the data scientist from the permutation tests? Permutation tests are useful heuristic procedures for exploring the role of random variation. They are relatively easy to code, interpret, and explain, and they offer a useful detour around the formalism and false determinism of formula based statistics, in which the precision of formula answers tend to imply unwarranted certainty. So one virtue of resampling, in contrast to formula approaches, is that it comes much closer to a one-size-fits-all approach to inference. So data can be numeric, or binary sample sizes can be the same of different. So assumptions about normally distributed data are not needed at all. So if I put it in much simpler language, permutation tests are a powerful tool in the data scientists' toolbox for making inferences about data when a traditional statistical assumptions may not hold, or when the distribution of the data is unknown. The basic idea behind permutation tests is to randomly permute the labels of the data, creating a null distribution of test statistics under the assumption of no effect or difference between groups. So the permutation tests are particularly useful in situations where traditional parametric tests are not appropriate, such as when the data is no normal, or when the sample size is small. So they can also be used to test hypotheses about relationships between variables, or to compare multiple groups or conditions. One of the main advantage of one of the main advantages of permutation tests is that they provide exact p-values without relying on asymptotic distributions, making them a reliable method for statistical inference. They also allow for the use of any test statistic, make them flexible and adaptable to a wide range of research questions. However, permutation tests can be computationally intensive and may require a large number of permutations to achieve sufficient power, particularly for small sample sizes. Additionally, the choice of test statistic and permutation strategy can impact the results of the test, requiring careful consideration and attention to the research question at hand. So overall, permutation tests are a valuable tool for data scientists, seeking to make robust inferences about their data, particularly in situations where traditional statistical assumptions may not hold or when sample size are so small. They provide a flexible and powerful approach to hypothesis testing and can be used to answer a wide range of research questions.